were discussing in previous lecture yesterday. So this is a aspect that I have given just for a comparison. If we are having a electron rich substrate, just like a simple olefin we have, if it is going to add to a electrophilic center, mean electron deficient entity, because electron rich can only react with an electron deficient center. So if it is reacting with this, arrow shall be like this. But what is the question? This electrophile approach in what direction? Either it approach from this direction, it approach from this direction, it approach above the plane, it approach behind the plane, or it approach angularly. There are various possibilities. How this electrophile approach electron rich center? This is the question. That's why molecular orbital approach has been able to explain this, because molecular orbital are very important. If you remember, this pi electronic density is transferred. First of all, we make it clear that whenever this type of additions are taking place, the pi orbital is important. Why? If you look at pi orbital, it is electron rich. Electrophile is electron deficient, no electron. So when these two electron and these no electron are overlapping, so they shall result in bonding 2 electron in entire bonding 0. Bond order shall be 2 minus 0 divided by 2 shall be 1. So bonding is possible between pi and electrophilic center. Fine. If let's say pi star is also there, if pi star interact, it has no electron. Electrophile has no electron. So where it shall be? They are not going to interact with each other because they are going to form 0 bond order. No electron in pi star, 0 minus 0 divided by 2, answer is 0. So that's why no bond order is possible if pi star overlap. But if pi overlaps with this, then there is a involvement. So the pi orbital have this geometry. If you remember, banana shape orbital, it is symmetrically distributed throughout the sigma bond. So this is the pi electronic density. Sigma bond is more stable, pi bond is less stable. If we look at the energy profile, sigma bond is underneath here and sigma star is over pi star. So anyhow, uh, interaction of pi with electrophilic center is giving you a significant interaction. So this is a significant molecular orbital, in other words, whereas pi star is not a significant molecular orbital. That's why we call this insignificant molecular orbital. It is not going to interact because it is giving you a 0 bond order, in fact. So I have enlarged this molecular orbital here in larger size, just to show that look at where is the maximum electronic density available. This is the point. You see the peak, this one and this one, where maximum electronic density is available. So electrophile shall prefer that position where electronic density is maximum. You see, if it is approaching this center directly from this direction, or this direction, there is no electronic density available here, pi electronic density, which means it is interested in. So this is having a nucleus. This nucleus is positively charged. This is already positively charged. So when if it is approaching from this direction, it shall repel back. If it is approaching from this direction or this direction, it shall repel back. Second, there are some alkyl groups present to the olefin. So that's why it is also making a steric hindrance. So alkyl groups present here, and similarly the nucleus, no electronic density around this, is repulsing this electrophile. It is not approaching this side. Electronic density is maximum present at this position and at that position. If I draw a tangent to this, you see I have joined just these two maximum lines. So it is perpendicular to carbon-carbon sigma bond. It means electrophile shall approach from this direction, or if I draw here, from this direction like this or like this. These are the two possibilities. It has equal opportunities approaching from above the plane, approaching from behind them. These are the two possibilities that this electrophile can approach. This is what you have seen yesterday. Now proceed further. This is the molecular orbital approach for carbonyl additions. You have already come across this system. If we have this oxygen, sulfur or nitrogen, this X is oxygen, sulfur or nitrogen. So in all such cases, this carbon is electron deficient. So electron deficient shall react with an electron rich entity, which we commonly call as a nucleophile. So this nucleophile shall approach this carbonyl carbon, and this electron pair density shall transfer towards X. Because this is more electronegative, it shall be happy to have a negative charge. So this is how it acts. Now again, there are two questions. It also have a pi bond. So these pi bonds have two orbitals. Look at here. It also have two orbitals, pi and pi star. Pi is occupied, pi star is empty. Now look at here. What is happening? Nucleophile is electron rich. It has two possibilities. It can transfer electron to pi. It can transfer electron to pi star. If it is transferring electron to pi, pi is already occupied. Nucleophile has two electrons. So what shall be, how many total electrons? 4. 2 shall go to bonding, 2 shall go to anti-bonding. What shall be the bond order? 2 minus 2 divided by 2, answer is 0. So as a result, if nucleophile approach pi orbital, it shall have 0 bond order. It means this shall be insignificant molecular orbital. But which shall be the significant? If nucleophile is approaching pi star, it is having 0 electron, no electron. Nucleophile has 2 electrons. So what shall be the bonding order? 2 minus 0 divided by 2. Answer shall be 1. So it means here this pi star shall be significant molecular orbital towards carbonyl addition. It is opposite what you have seen for olefinic system. So it means this is the orbital that I have presented. This is a carbon-oxygen bond, not carbon-carbon. In previous, we have seen carbon-carbon bond. So it is symmetrically maximum at this position, but here it is opposite. You can see in this case, we are having carbon-oxygen bond, in fact, in which we are having these orbitals. These are the 4 orbitals that we are having at the moment. So in this case, now you see where is the maximum electronic density available. This is the maximum electronic density available. Here maximum electronic density is available. Here is maximum and here is maximum. These are the 4 positions. Now look at two possibilities are these. It is approaching from this direction. Nucleophile is approaching from this direction. Fine. Now it can also approach from this direction or that direction. But do not forget this oxygen is already electron rich. It has 2 non-bonding electron pair. One is this non-bonding electron pair, other is this non-bonding electron pair. When oxygen has these 2 non-bonding electron pair present on this, it shall in fact repel this nucleophile, because this is electron rich lone pair repulsion. This negative charge on nucleophile means this is an electron pair. This electron pair is charged. This electron pair and these electron pair shall repel each other. So they are having a repulsive forces. Similarly, this nucleophile shall also approach. If it is approaching here, mean it is making a bond with what? It is making a bond with oxygen. Oxygen is already electron rich. Due to partial variation, due to this charge separation, it is more electron, partial negative, partial positive. So nucleophile is negatively charged. Oxygen is also negatively charged. So they shall repel electrostatically to each other. Second, there are lone pair repulsions present here. That's why nucleophile shall not approach this side or this orbital. It is not going to approach these two sides. That's why these are insignificant interaction of the nucleophile with these two. It shall not interact with this due to steric hindrance. Second, if it is overlapping with this, it is making a bond with oxygen. Nucleophile is electron rich. Oxygen is already electron. Is no two electrons which can interact with each other. So here nucleophile is electron rich. Carbon is electron deficient. It shall prefer to approach here because there are electrostatic forces of attraction. So carbon and nucleophile, they are having electrostatic interaction. That's why it shall approach here. If it is approaching from this direction or it is approaching from this direction, it has equal opportunities. If it is approaching from this direction, it is making a bond with carbon. If it is approaching from this direction, it is making a carbon bond. So it means both are the possibilities. But if we look at this angle, where it is approaching here, this angle starting from here to here, this is exactly 107 degrees. This is not 120 degree. Theoretically it looks like, but diagrammatically I tried my best to draw this orbital, but it apparently looks like this is the half of this 90 degree. This is the half of 90. It is not the half of 90. It is slightly tilted toward this side. So it is 107 degree angle in fact. So if I draw this angle, these orbitals, it is slightly towards this. So we are not measuring this angle. We are measuring this angle. This angle. This angle is 107. Similarly, this angle, this one, this is 107 degree. So when a nucleophile approach, it approaches 107 degree angle in fact. So this is the reason it has two faces. One face is this, other face is this. If it approach from here, it shall be a different isomer. If it approach from here, it shall be a different isomer. Just focus here. If you remember the nomenclature you would have come across in previous semester in stereochemistry, let's say we have this oxygen, this alkyl group is above the plane, this hydrogen is behind. According to CIP rule, this oxygen shall have highest priority, this R group shall have lower priority, and hydrogen shall have least priority. If we look at here, this is the first, this is the second, and this is the third. So it is having a anti-clockwise rotation. So when we are looking at this molecule from this side, it is the side phase. If we are looking it from the back side, then we shall have these two opposite. Now hydrogen is on our right and R is on our left. When we shall looking it from the opposite side, this R shall be right and this hydrogen shall be left, opposite. So this shall be first, second, third. It shall be a R clockwise rotation that we call reface. So this is the clockwise one is called reface and anti-clockwise one is called side phase. So it has two possibilities. One is through another is through side phase. So these are the two aspects that is very important to undergo. But you are also very important to understand what is our nucleophile. Until and unless the nucleophile is not clear to you, we cannot proceed further. So let's first define what is a nucleophile. I have written in the blue on the chalk, such soft bases, keeping in mind it is a soft base. Soft base. What is a soft base? You have studied the soft and hard acid base concept. A base is always, this is a Lewis base, electron pair donor. But what means by soft? Soft means it is being explained later. What means by soft? So such base mean electron pair donor, mean it is a Lewis base which carries a negative charge or a non-bonding electron pair on a low electronegative atom with low charge density are called nucleophiles. So what is a nucleophile? Any entity which is electron pair donor. And what can be electron pair? It may be a charged electron pair or it may be a non-bonding electron pair, just like you have a non-bonding electron pair present on nitrogen. So that shall be a non-bonding electron pair. Maybe you have a halogen having a negative charge on it, so that shall be treated as a negative charge. So this is a just variation in these cases that you are supposed to make it clear that it may be an electron pair charged or it may be non-bonding electron pair present which can be donated. It shall be a base. But what kind of base? A base where negative charge or a non-bonding electron pair is present on a low electronegative atom, and it has a low charge density. I shall explain what these two terminologies are. If you remember, if we are moving in the periodic table, boron, carbon, nitrogen, oxygen, fluorine, and there is a helium next, sorry, not helium. So these are noble gases. I have avoided that because that doesn't participate in reactivity. So if we are moving from left to right, what is happening? Electronegativity is increasing. This one presented in red, En stands for electronegativity. If we are moving from boron to fluorine along the period, what is happening? Electronegativity is increasing. So Cd is standing from charge density. What is charge density? Charge density is just like a density. Density is mass per unit volume. So what is charge density? Charge density is number of charges on a molecule or atom or an ion divided by the volume it occupies. So if we are moving from left to right, if we are moving from left to right, the atomic radius is decreasing. So let's say we have a negative charge on carbon, mean carbonine, one negative charge on nitrogen, one negative charge on oxygen, one negative charge on fluoride. So all of them have one charge, which is same. So one charge divided by volume mean ionic radius. So ionic radius of carbon is larger than nitrogen. Nitrogen size is larger than oxygen. Fluoride have smallest size. So it means volume is lower, so it shall have a high charge density. So if we are moving from left to right, in other words, we can say charge density is decreasing if we are moving in this direction. So charge density is in fact charge per unit volume. If the unit area is increasing, so I have made this opposite. This arrow should also be opposite because charge density we are bringing in this direction, not the atomic radii. I have presented this with respect to atomic radius. Atomic radius of carbon is highest, boron is highest, then carbon has lower atomic radius, then nitrogen, least one is fluoride. So this is not Cd, this is not charge density, this is just replace this Cd by atomic or ionic radius. Ionic radius. So ionic radius is increasing from right to left. For electronegativity is increasing from left to right. This is ionic radius. So what it shall influence on uh, charge density? Because the volume is decreasing from left to right, so charge density shall increase. It shall be having the opposite direction. But this is for ionic radius. Ionic radius is decreasing when we are moving from right to left in the period. But if we are going opposite, if we are moving down the group, if you remember what is happening down the group, the electronegativity is decreasing. Or we can say if we are moving from bottom to top, the electronegativity is increasing. So electronegativity is increasing from bottom to top of the group, and in a period this is opposite, from left to right electronegativity is increasing. So atomic radius, if you see from fluorine to iodine, this is increasing. Why increasing? Because the shell is increasing. So ionic radius is increasing down the group, and what it shall influence the Cd. So when we are moving down the group, the atomic radius is in fact increasing. That's why charge density is decreasing. So if we have a negative charge on iodide, we have a negative charge on bromide, chloride, and fluoride. Fluoride is the strongest, or you can say smallest negative charge on this. In iodide, it shall be largest atomic radius, but charge is same. Radius of iodide is larger, so it shall have lowest charge density. Iodide shall be the best nucleophile, and fluoride shall be the good base, but not worst nucleophile it would be. Fluoride ion the strongest base. It is not a good nucleophile. Iodide is the best nucleophile among them. So this is how you can justify looking at the periodic table, how we can justify which one. If we are comparing oxygen versus sulfur, sulfur negative, negative charge on sulfur and negative charge on oxygen. Sulfide shall be a better nucleophile than oxides, just like we have alkoxide ions. So in comparison to this, we are having sulfides are better nucleophile rather oxides. So similarly, non-nucleophile we can divide into three categories. One is a hard nucleophiles, other are soft nucleophiles, and some are borderline cases. In some cases, they act as a hard, in some cases, they act as a soft nucleophiles. Now, if I present here hard nucleophile, I presented fluoride. So fluoride and chloride both are hard. Fluoride is the hardest. This is the order of hardest most is fluoride, and then it is decreasing the level. So fluoride ion is the hardest, then hydroxyl ion. We should put a negative charge on this alkoxide ion as well. Negative charge is missing. So OR, we shall have a negative charge here. This is alkoxide ion. So alkoxide is a better nucleophile than hydroxyl ion. Hydroxyl is a better nucleophile than fluoride. Fluoride is a simple base, it is not nucleophile. Water is a better nucleophile than alkoxide ion. And alcohol is better than water. Chloride is a better than all of this.